Okay, it's time. So we will be recording this. Are you happy with that? Okay. So I'll start, and we'll edit it for until now. Okay. Hello, everyone. Welcome. So lovely to see a huge group of physics students joining us for this talk. Thank you to everyone who's joined us online. It's my pleasure to introduce for the first time in our research seminar series our newly recruited colleague. I'm still going to call you new probably for the next 10 years, but newly recruited colleague, Dr. Walid Malaeb. The title of his talk, as you can see, is on it's a small c. Hey, now it makes sense. Okay, it's on superconductivity, uncovering the underlying physics using photoemission spectroscopy. And as usual, we look forward to having a little bit of time for Q&A after your talk. So when you're ready, the floor is yours.
So good afternoon. Thank you, Dean Jnainati, for the introduction and for your continuous support and motivation. I also thank the organizers of this series, especially Dr. Harmanani. He was very patient with me regarding the time and date. Thanks for the attendees, especially our great students. Today I'm going to talk about high-TC superconductivity, but given that we have maybe a diverse audience, I try to make it somehow general and maybe skip some technical details. So what is superconductivity? If we have a look at a normal metal, for example, copper, if we cool down, reduce the temperature, so we notice that there is a reduction in the resistivity until we reach around 0 Kelvin, when we end up with some residual resistivity coming from impurities and imperfections and so on. However, in a superconductor, for example, mercury, we notice an abrupt drop in resistivity, and that was discovered back in 1911 by Onnes, and these were the original data, of course, and this is if you take a superconducting wire and you induce the electricity in this wire, it will go on forever. So that's the first property of superconductors, and actually it makes 50% of the identity of superconductors. The other 50% comes from the magnetic identity, which we call the Meissner effect. We have total expulsion of the magnetic field from inside a superconductor, and this results actually in what we call perfect diamagnetism. And this is the famous levitation phenomena. Probably this is the most famous photo you're going to obtain if you go to search engines and you put superconductivity. So this is a magnet flying above a superconductor. Well, regarding applications, of course, these two phenomena, we can use them first for power transmission. Imagine that you have zero resistivity, so you can transport electricity with no loss, of course. This has an advantage over the conventional copper wires we use nowadays. And levitation is used in transportation to make the maglev, which is the flying train, which is being developed and tested in Japan. And actually, I visited the site in my last visit in December. They made much progress, and they are expected to make this commercially available in 2027. Well, I have a zero resistance, a large current, so I can produce a large magnetic field. Means I can use it in MRI, magnetic resonance imaging, for example, in particle accelerators, and even in the SQUID, the superconducting quantum interference device, to detect very weak magnetic fields, including the waves we produce, as we think from the human brain. This is a very optimistic and ambitious chart regarding various applications of superconductivity. But of course, this should make us very happy. However, this is still not so possible because we need very low temperatures, and we still, of course, have many obstacles, especially technical issues to full application of superconductivity. Okay, regarding the history, just to be a little here focused on the copper oxides, which is the first family of high-TC superconductors discovered in 1986 by Bednarz and Muller, and of course it led to the Nobel Prize. And after that, we had some discoveries until the year 2008, where we witnessed the discovery of iron pnictides, or iron-based superconductors, by Kamihara and Hosono at Tokyo Institute of Technology. So that was the second family of high-TC superconductors. So now we have two families, the copper oxides and the pnictides. And let's see how the story goes. So the discovery was reported on 23rd February 2008 in this paper, and it initiated what we call the iron era. It made like, it had like rapid worldwide recognition, and it became kind of a national project in Japan. Here are usually messages even from the Prime Minister for the conferences on that topic back in 2008. And Hosono, the professor who joined this discovery, he used to say, strike while the iron is hot. And this is what we did actually when we started our research on these new materials back in April 2008, just 2 months after the discovery, after the first report. We received samples from the discoverer, Kamihara, and the first data were taken in April and May 2008. And the first manuscript appeared online in June, just 4 months after the discovery. Okay, so as I mentioned, you have a new family of high-TC superconductors. The first thing you want to do is to compare with the previous family, which is the cuprates. Starting from the crystal structure, they have a very similar crystal structure, a layered one. Very similar phase diagram means, okay, this superconducting dome and antiferromagnetic order and so on. I will skip some details here. And the plane that hosts superconductivity, it is the iron arsenic plane here, it is the copper oxide plane here. So there are some similarities, and actually the antiferromagnetic order is the main thing here. Of course, with time, we got to know more and more details. However, at that early stage, there was an urgent need to uncover the electronic structure of these materials. And this was our starting point, where we started this study using photoemission spectroscopy. What is photoemission spectroscopy? Just to give you a brief idea, here are many references. So it is simply based on the photoelectric effect, which was discovered by Hertz back in 1887 and explained by Einstein in 1905, which led him to the Nobel Prize in 1921, actually, and based on the law of conservation of energy. So you have a sample, light falls on that sample, ultraviolet or X-ray. We remove the electrons. We call them photoelectrons. This is the photoelectric effect. We collect these electrons. We measure their intensity. We measure their energy and momentum. Then we reach a understanding, or this provides us deep insights into the electronic structure of solids. This looks very easy. You have access to the valence band, conduction band, and so on. But actually, this is very complicated at the technical level because you need a vacuum chamber. Your electrons, the photoelectrons, must not interact with anything before we detect them. Right? So you need a vacuum chamber. Of course, you need cooling and so on. You need very complicated detector, analyzer, and you need radiation. So this radiation is usually obtained from the synchrotron facilities. These huge particle accelerators that accelerate electrons to very high speeds, comparable with the speed of light, then the synchrotron radiation is obtained. And of course, this is some history about it. And this is an example of a huge ring. This is Spring 8 in Hyogo Prefecture, Japan, where this is, I think, the largest synchrotron facility in the world. So these facilities actually allow us to do photoemission spectroscopy. And here I summarize the main facilities I have been using since 2006 in Japan, in Stanford, and in Berlin. Well, I just selected a few examples to show you how we really uncovered the electronic structure of iron pnictides using photoemission spectroscopy, starting with the first report. That was the first report we did on iron pnictides in 2008. So we usually, just to give you a brief idea here, we are interested in the electronic structure near the Fermi level, because these electrons are the main players, the contributors in superconductivity or some other exotic phenomena. So interestingly here, we noticed that iron, Fe3D, was the dominant component near the Fermi level, which means that the name iron pnictides is very convenient. So iron pnictides or iron-based superconductors. So that's okay. However, that's very strange because iron is magnetic, and magnetic materials actually are the enemies of superconductivity. So they tend to kill superconductivity. However, this magic recipe, sometimes we call it, of iron and arsenic, and this structure actually made iron to make a constructive role in the phenomena of superconductivity. That was our first report, and of course, we did like some detailed study about the bandwidth and so on. And here, interestingly, we noticed that the degree of electron correlation, so how much these electrons interact with each other, represented by this factor here, 1.8, was larger for higher TC. So that was important information at that stage. A few months after that, the single crystals became available, and we did the more detailed study, which is the ARPES, angle resolve study, for this compound. And here we presented like the Fermi surfaces near the beryllium zone center with hole-like bands, near the beryllium zone corner with the electron-like bands, and so on. And using the advantage of the synchrotron radiation, we varied the photon energy. This allowed us to probe what we call the KZ direction. So we checked the photon energy dependence. I'll skip the details. And I'll just show you that we had a strong KZ dependence, which means that the Fermi surfaces along the KZ direction, they vary a lot. So this was a new, this kind of a new property revealed by a high TC superconductor. So we know from caprates that only two-dimensional materials host high TC superconductivity. So this was very new regarding these materials. This is a summary of that work. Then after that, we wanted to study the superconducting gaps. So what do I mean by superconducting gaps? So far, we know only about one full microscopic theory of superconductivity, which we call the BCS, Bardeen, Cooper, and Schrieffer. And this tries just to understand the superconductivity in conventional materials. So it talks about pairing of electrons. And that's actually very strange, because electrons usually tend to repel. They have a similar charge. However, there is some interaction with the lattice, as you can see here, like the positive ion cores or some other source, which kind of give energy for the electrons to pair. So now I have a Cooper pair, and I have many pairs, which make a coherent state, and this is superconductivity. So the idea was suggested back in 1957, and of course it led them to the Nobel Prize in 1971, but that theory was limited. So of course it expected a universal behavior only for conventional superconductors. So the materials discovered in 1986 and 2008, the BCS theory doesn't work here. So we still actually don't have a full theory. Anyway, so this theory, given that we have pairing of electrons, then we expect a superconducting gap. And this superconducting gap can be observed experimentally by photoemission spectroscopy. As I show you here, a brief idea, an example. And we care about what we call the superconducting gap symmetry. So understanding how these electrons pair leads us to more understanding of the pairing mechanism, the superconductivity itself, and makes a kind of roadmap. What is the condition to get high TC superconductor? So that's why understanding the gap symmetry is important, and this is what we did actually on the new iron-based superconductors using laser ARPES, advanced lasers at the Institute of Solid-State Physics in the University of Tokyo. And this is very low energy, 7 eV. It has many advantages over the synchrotron radiation. And here is an example of how we can see the superconducting gap. Of course, I will not get deep in the details, but just to show you here, this intensity, the lack of intensity here means the opening of the gap. So this continues all the way below TC. As far as the material is still in the superconducting state, when it goes to the normal state, no more superconducting gap. And of course, usually people plot this gap versus the temperature, and it shows kind of behavior similar to the BCS, but with some differences in the pairing strength and so on. So that was, okay, this is just an example of how we can measure the gap, but we did a full study actually for a wide doping region, means for different TCs. So we were investigating how does the gap affect TC on different Fermi surface sheets. And of course, we noticed that one of the Fermi surface sheets doesn't contribute. Why is that? Because, okay, we extended the study and we investigated the Fermi surfaces here, and it was like some change in the beryllium zone corner, at the beryllium zone corner. Yeah, I'm glad to show you here results just from last year. this interesting review in Nature. So there is still a debate about the superconducting gap. I mean, back 10 years ago, we measured experimentally superconducting gap, but still the idea is still open for discussion. The gap is related to the Fermi surface shape and so on. So this is still under debate, under discussion. One more thing we studied was the kink and the mode coupling, and here I usually like to show a figure from the textbook, the famous solid-state physics book, the Ashcroft and Merman. So back, I think, in the 60s, so they show you the electron band, and if there is some additional interaction, it shows an anomaly. This is what we call the kink, usually. So this is due to some change in the self-energy and so on. And this study was done for the copper oxides, for cuprates, back in 2001, 2006, and so on. We wanted to investigate the same effect for the newly discovered iron pegmitides. And that was done with the laser. We did a detailed study here. We checked how is the dispersion behaving, and actually it shows a very clear anomaly here, a very clear change in the slope, which we interpreted as kink 1. And we tried to find the energy at which this kink occurs, this anomaly occurs. This energy will be referred to as omega, here, omega. And we also observed another kink. This is not enough. We went to this is some more detailed analysis. We checked also these results at the synchrotron. So laser and synchrotron, just to give it, to have more confidence in our results. And we could reproduce the data. That was in Hiroshima, ISOR. And of course, we did a full study, various TC and various energies for the kink. And we noticed something very interesting happening here. So one energy scale is related to TC, is related to superconductivity. However, the other energy scale, which we call kink 2, is not related to superconductivity. You see the data maybe here plotted in a better way. So relating this mode energy with the gap size. And it showed a linear behavior and so on. But what is the importance of these results? First, they agree with other experimental data that were available at that time, scan tunneling microscopy, inelastic neutron scattering, and so on. And I plot them overlap the results. Very nice agreement. And that, after all this, gaining all this confidence in these results, we reported the first evidence from ARPS, angle resolved photoemission spectroscopy, of a universal relation between the mode energy omega and the superconducting transition temperature. So now we have kind of indication that there is a mode, even if we don't really understand this mode, but this mode is somehow related to superconductivity. So this is what I mean by deeper insight about the origin of the mechanism of superconductivity. So gradually, you see, with the years, we gain a better understanding of this phenomenon. We proceeded also in studying more anomalies in the electronic structure. I'm not getting into the details here. Of course, better understanding. And here I'll talk a little bit about what we call the pseudo gap. So far, pseudo gap. Okay, so far I mentioned, maybe the guys working on this topic now are happy with the details. Their senior project is on this topic. So we have electron pairing, but this occurs only in the superconducting state. And it is responsible about the phenomena of superconductivity. Great. But we noticed also that above the TC, in the normal state, we also have pairing, but it doesn't lead to superconductivity. So that was strange. We call it pseudo gap. And some people, there are two schools here. Some people believe that it is directly related to superconductivity, but there is no coherence. That's why the word coherence is very important for us. Some other people believe that it's against superconductivity. So we did this work actually also with Kamihara, the discoverer of iron pegmitides, and we investigated using this a new sample, a new system, and we investigated the pseudo gap, this gap at room temperature. And again, we are sure that we have a pseudo gap. So pairing starts at high temperature, but somehow it doesn't lead to superconductivity. That's also important information. To make us look, to know where to look regarding these materials. Well, I think that's about the photoemission part. So I showed you some examples how we can get a deeper understanding of the physics using the photoemission spectroscopy. Another research topic is improvement of the superconducting properties of iron pnictides as well, with nano-sized particle additions. So actually this project we started also in collaboration with Kamihara, the guy who discovered these materials. Now he's in Keio University, and I hope that and this project, unfortunately we couldn't proceed with this project due to COVID, so I hope now the time has come to continue the collaboration, but initiate this kind of research here at LAU. This is what we are looking for. So the motivation for this study, in the unconventional superconductors, we usually have something called vortices. Maybe the word is familiar, the vortices. So these are quantized magnetic field lines that exist in the superconductor. And they are moving, actually. They are not stable. So this reduces the efficiency of the superconductor and causes troubles, actually, because it consumes energy. It consumes energy, and we need to pin this flux. So the flux pinning is preferable to achieve better performance. And usually people look for what we call artificial pinning centers. And one way is to add the nanoparticles, because they do not interfere with the structure itself. They do not change the structure, but they act as artificial pinning centers. So why we are confident about this point? Because we tried it for the copper oxides, for the previously discussed family, high TC family. So in this compound, also in collaboration with Kamihara, and it showed positive results. So we could really achieve improvement in the superconducting properties. That's why we will do a similar work for iron pnictides. Of course, for iron pnictides, it's more challenging because you have first to prepare the system and then add the, each challenge is a thing by itself. So anyway, we did some work on that project. So we prepared this iron-based superconductor at Keio University with Kamihara group, and we could reach the phase, so judging from the X-ray diffraction data, and we could also see very nice superconducting transition, as you see here. So these are the experimental results, and this is also confirmed not only from resistivity, but also from magnetization. So this transition, so 50% and 50%. So we completed the ID of our new superconductor. So the next, and okay, we stopped there. So I call these like preliminary results. Now it's time to initiate this project again, to try to add the nanoparticles and see their effect. So there are a lot of things to be done here. For example, changing the impurity content, changing the lanthanide here. So this can be a long project, actually. And I hope we will have the infrastructure and the funding to do this here at LA. This is my next target, actually. Moreover, third topic is about the photoemission studies on superconductor and ferromagnet heterostructures. So this project, actually, we started last year. It was funded by Japan Society for the Promotion of Science, JSPS, and I consider this to be the first real collaboration between LAU and the University of Tokyo. Thanks for Dij Neinati for the article, and for Luther also for a very nice article talking about this thing here, what we did in Japan. That was through JSPS fellowship. I was hosted by Professor Kobayashi for 2 months, December and January. And the main purpose was to study the electronic structure of these heterostructures. What do I mean by heterostructures? This is an example. So we have, so all what I've been discussing so far talks about bulk materials. Bulk, the material as you see it. However, here, people are trying to make thin films, layers, right? And they grow layers of superconductor over ferromagnets, semiconductors, a lot of diverse variety of materials. And they check what happens. So what happens is that what we call proximity effect. So interaction between the superconducting layer and this ferromagnetic layer. At the junction itself, there is kind of exotic physics, new physics that we need to understand from one side. And from the other side, this has a great potential for applications. And I'll show you a little bit of examples here. So maybe for the physics students, before we discussed about spintronics, is the spin plus electronics. So here you are adding one more degree of freedom, which is the spin. Usually in the conventional electronics, we have the charge, the flow of electrons. Here, you want also to make use of the property of the electron, which is, or the charge in general, which is the spin. And actually at the University of Tokyo, they have this Center for Spintronics Research Network. And this is the center that hosted me actually in my previous stay. And I borrowed this slide from my friend and collaborator, Professor Kobayashi. Is so excited about it. So the thing is that in that center, basically we have engineers that are trying to make new devices for spintronics. And we physicists come there and help them understand the physics, what is happening inside. So I'll give you an example about the recent results we got there. Here I show you some example, part of the results. Sorry, it's like under the data is under analysis, under discussion, kind of still confidential. We're writing the manuscript, but I'll just show you an example about it. This is the X-ray photoemission spectroscopy machine that we used for getting some data. The samples were provided from there, from that center. XPS and ARPS performed there. So here, you see the layer is only 25 nanometers. And remember that 1 nanometer is 10 power minus 9 meters. So that's why people are talking about nanotechnology, 10 power minus 9. So this is a very thin layer, okay? So just to give you an example, I went to the guy and asked him about the sample. Is it ready? He said, I still need 5 more minutes. So why 5 more minutes? Because, so they have their own calculations. 1 minute leads to 1 nanometer thickness, okay? So they just form the layers, any thickness we want. And actually changing the thickness changes the physics. So this is still under investigation. So what we did here, just to show you an example, we studied like the as-grown sample as it is. We annealed it at 100 degrees Celsius and 200 degrees Celsius. So in the end, you want to use these samples in devices, okay? And you want to be sure about their stability and performance at different temperatures. So I don't like, it's not the physical status of the material, like it melts, it doesn't melt. That's not the target. You need to understand the electronic structure. What's happening there? How do the electrons interact with each other and with their surrounding? So here we show an example, like the material is stable from the electronic structure point of view up to 100 degrees Celsius. And then some changes happen. This is near the Fermi level, and also we investigated deep inside the core level. So we see some shift towards here probably higher or lower binding energy. It depends how you see it, the angle. So the change in the structure of the surface and so on. So this is very important information regarding the potential applications of these materials. We have a lot to do there. This project is just started. We started last December. And I hope we can proceed in this project as well. And here we show, this is very rough data, but it's the ARPS results. Guys, I think you know about Dirac, okay? You know about Dirac, and we have what we call Dirac cone. Sometimes the electronic structure shows a cone. So there is intersection in the bands, and this point, we're looking for this point. And there are like some exotic states like Majorana fermions and so on. So we could roughly observe the Dirac cone in these preliminary measurements. I hope also to proceed with this. So all in all, I showed you examples about the successes of photoemission spectroscopy and its ability to give us insights about the electronic structure of high-TC superconductors, especially iron pnictides. Then I showed you about a project to improve the superconducting properties of iron pnictides. I hope we can do it here at LAU. And finally, a project about heterostructures, superconductor built or grown above several layers of ferromagnets and so on. Thank you.
Thank you very much, Dr. Malaeb. Really fast-paced and thoughtful presentation.